Hey there. This presentation is designed to give you an example of how to use stoichiometry to calculate theoretically how much product can be made in a chemical reaction, and to identify which of the reactants is the one that gets used up first and the one that is controlling the reaction. And then also to identify or calculate something called a percent yield. So for this assignment, I would like you to copy down these notes and examples. I want you to write everything that's typed on the screen, and I also want you to write what I write. It is best if you do this while watching the YouTube video that goes with this, so you can see the problems being solved. And then I'm going to want you to take images of your copied notes and examples that are in this presentation and submit them in Schoology. Your second assignment this week is going to, you're going to be asked to solve one problem. The previous assignment you had 5 problems, and this you're going to have to do one problem, but the one problem in and of itself has 4 questions, so it is a little bit more involved. It's much more involved, which is why I'm only going to go through one example in this presentation today. So that will be available later this week. So the essential learning goals, excuse me, it's nighttime and I'm probably going to yawn a little bit. It's probably going to happen. The essential learning goals is to be able to use mass-to-mass stoichiometry calculations like we've been doing to identify the limiting and excess reactants, also calculate theoretical yield, and calculate percent yield. And it sounds like a lot, but most of you have been handling stoichiometry like a champ, and I can promise you it's really not that much difficult. It's more difficult. It's like what you've been doing with a little bit of a twist. So what I have written in the red is not anything necessarily that you have to write down. So first of all, talking about the limiting reactant, this is the reactant that limits how much product is going to form. Now you may end up having to pause this presentation a little bit because I'm probably going to read through it faster than what you can write. So if you need to pause it, then you should pause it and write down, give yourself enough time to write down during this presentation. So limiting reactant reacts or limits how much product will form. Now the amount of product that forms is called a theoretical yield. It is theoretically what the math tells us is the maximum amount of product that could form in a chemical reaction if all things go smoothly in the lab and the reaction goes to completion. So there are lots of things that can get in the way of you carrying out a reaction in the lab and actually collecting the theoretical amount of product that could form. So you could lose product. Sometimes things get washed down the drain. Sometimes things spill. If that happens, you're going to get less than what you could have theoretically gotten. Sometimes you may not clean your product good enough. There might be some impurities left behind or some water. Your product might not have completely dried yet. So when you take a measurement of that product, it might seem like you have more than you could possibly theoretically have because of other stuff that might be in there. So when the limiting reactant is all used up, the reaction stops. What happens is you have your products and oops, so sorry. Probably a little bit of unused excess reactant. And limiting reactant problems start with 2 numbers. So in the previous problems that you've only seen 1 number. This time we're going to start with 2 numbers. So we have to do 2 mass-to-mass stoichiometry problems. And the answer to the problem is whichever of those two calculations gives you the smaller amount. Just like when we had a loaf of bread, I don't remember the numbers, we had a loaf of bread with 22 slices, we had some peanut butter with 37 servings, and some jelly with 48 servings. With that combination of things, we could only make 11 sandwiches. So 11 was the smallest possible number. So that was the limit. That was the maximum amount of sandwiches we could make. Now, if you drop a piece of bread on the ground, theoretically, we could have made 11 sandwiches out of 22 pieces of bread. But let's say you drop one on the ground, and all of a sudden, what you can actually produce is different than what you theoretically could have, because something went wrong. Percent yield is the amount that it's the percent retrieved. So if you carry out a reaction in the lab, it doesn't always go as planned. If we weren't learning remotely right now, at the time of this that this video is being made, we would be carrying out these reactions in the lab, and you could be doing your own experiments with percent yield. So actual yield is the actual amount that you collect and measure in the lab. Again, sometimes you might lose some of the product through a spill or getting left behind in a filter, or some accidentally spilled down the drain. The reaction might not go to completion, and sometimes you might have some impurities. So a percent yield calculation is the actual yield divided by the theoretical yield times 100. So a sample problem is going to ask 4 questions. And for this scenario, we have this reaction in which we're combining some iron 3 oxide with hydrogen chloride, and we're making iron 3 chloride and water. And we want to theoretically know how much of this iron, how much of this iron 3 chloride product we could theoretically produce if we start with 206.9 grams of iron 3 oxide and 210 grams of hydrogen chloride or hydrochloric acid. So to do step 1, there are going to be 2 mass-to-mass calculations. This is going to be your first A, and this will be your B. This will be your second A, and this will also be your B. And then whichever product, whichever of the 2 calculations gives you the smaller number, is the theoretical yield. Then we have to identify which reactant is the limiting reactant. It's whichever one gave you the smaller grams of product. So the excess is just going to be the other. It's going to be the one that gave you the greater grams of product. And then you'll be given, since you're not carrying this reaction out in the lab, you'll be given an actual yield, and we'll have to calculate a percent yield. So this next slide is just for you to visualize what the problem is going to look like. So just for you to look at and visualize what the problem is going to look like. So to solve, we need 2 mass-to-mass calculations. The first mass-to-mass calculation is going to be from your first reactant, and the second mass-to-mass calculation is going to be for your second reactant. And we want to figure out how much product we're going to make. So in the mass-to-mass calculation, it's set up like this. You start out with the number that's given. We're trying, and this is our A, so we have an A1, we have an A2, and here we have the same B. Now, whichever of these 2 answers is smaller, so I don't remember which one is smaller off the top of my head. So theoretically, I'm going to say that this ends up being 10 grams of iron chloride, and this ends up being 13. then this would be my theoretical yield. And this would be my limiting reactant. And this would be my excess reactant. Now, again, I don't remember off the top of my head what this ends up being, but we'll find out on the next slide when we go through the problem. So I have the question here. What will the theoretical yield be if when 206.9 grams of iron, or Fe2O3, reacts with 210.4 grams of HCl in this equation? Which reactant will be the limiting reactant, which will be the excess reactant, and what will the percent yield be if 298.5 grams of iron 3 chloride, or FeCl3, is actually collected? There seems to be a weird little typo there. Okay, so I have the same map up here that we used with mass-to-mass calculations. So I have 206.9 grams of Fe2O3. I have 210.4 grams of HCl. So this is going to be my A1, this will be my A2, and it's asking about this, so this is going to be my B for each of them. So I have 206.9 grams of Fe2O3, and I'm solving for excuse me, solving for grams of FeCl3. That's going to be my first problem. My second problem is going to be starting with 210.4 grams of HCl, and also solving for grams of FeCl3. So this is my A. In this first step here, I have 1 mole of A on top, which is wherever I have A, I'm going to put Fe2O3. The molar mass for A is 2 times 55.85 plus 3 times 16, and it ends up being 59.7 grams. So 159.7 grams of Fe2O3. The next step is my multimole ratio. I have moles of A on the bottom, which is Fe2O3. I have moles of B on the top, and B is FeCl3. In front of Fe2O3, I have a 1, and in front of FeCl3, I have a 2. And the last step is 1 mole of B on the bottom, FeCl3, and it's going to be the molar mass, FeCl3. So we have 55.85 plus 3 times 35.45, and that gives us 162.20 grams for the molar mass. So 162.2 grams. Okay. On the bottom, I'm going to wait to do the math for just a little bit. On the bottom, with my new A, I have 1 mole of A, which is HCl. Has a mass of 1.01 plus 35.45 is 36.46 grams of HCl. And next is our multimole ratio. I have moles of A on the bottom, moles of HCl, moles of B on the top, moles of FeCl3. I have a 6 in front of my HCl, and I have a 2 in front of my FeCl3. And 1 mole of B, which is FeCl3. has a molar mass of 162.20 grams of FeCl3. So in the calculator for this one, I'm going to punch in 206.9 times 1 divided by 159.7 times 2 divided by 1 times 162.2 divided by 1 equals, and it ends up being 420.3 grams of FeCl3. For this calculation in the calculator, I have 210.4 times 1 divided by 36.46 times 2 divided by 6 times 162.20 divided by 1 equals, and that ends up being 312.0 grams of FeCl3. So what this means for us, this is the smaller number. So this is the answer. This is the theoretical yield. And that answers the first question. What will the theoretical yield be when we combine these two amounts of our reactants? Now, whichever substance gives us the theoretical yield is, I don't know what happened, I lost my pen, is this HCl here is, I'll go down here, this is the limiting reactant. So the limiting reactant is the one tied to the one that gives us the smaller number. By default, that makes this the excess reactant. So we have just answered our next two questions. Which reactant will be the limiting one? Whichever answer gives us the smaller number, whichever substance produced the smaller number is our limiting reactant. Whichever one makes the bigger number or the greater number is tied to the excess reactant. And then the last question, what will the percent yield be if 298.5 grams of FeCl3 is actually collected in the lab? So remember that our theoretical yield is 312. And this is the calculation here. I want to change the color. My pen doesn't seem to be working. Okay, I'll try it again. Okay. So if I go back to the previous slide, 312.0 grams of FeCl3 was my theoretical yield. The actual yield is given in the problem. It says, what will the percent yield be if 298.5 grams of iron 3 chloride is actually collected? So the percent yield will be the actual yield, which is 298.5 grams, so of FeCl3 divided by the theoretical yield, 312.0 grams of FeCl3 times 100, and it ends up being a 95.7% yield. Ideally would be 100% yield. Ideally, we would start with a certain number of grams of reactants, and we wouldn't lose any of the reaction, would go to completion, and we would get as close to 100% to this 312 grams as possible. But sometimes things go wrong, so we have to calculate a percent yield. So I would like you to take a picture of the notes that you've taken here and submit that. And then you'll be given one assignment later this week. You'll be given a problem very similar to this where you have to answer the 4 questions, and you will have to do work that looks like this. I will provide a balanced equation for each thing, but you will have to calculate molar masses. Now, the good news is I'm going to use all of the same equations that were used in the last assignment, so you will have all of your molar masses calculated already. So, thanks for watching.